In the realm of quantum computing, a fundamental challenge is efficiently simulating quantum circuits on classical computers. This paper introduces a novel theoretical approach that achieves exponential speedups over existing simulators for a wide class of quantum circuits. The technique leverages advanced group theory and symmetry considerations to map quantum circuits to equivalent forms amenable to efficient classical simulation. Several fundamental theorems are proven, including a generalized Gottesman-Knill theorem, which establishes the mathematical foundations of this approach. The potential of this method is demonstrated through theoretical analysis and preliminary benchmarks. This work contributes to the understanding of the boundary between classical and quantum computation, provides new tools for quantum circuit analysis and optimization, and opens up avenues for further research at the intersection of group theory and quantum computation. The findings may have implications for quantum algorithm design, error correction, and the development of more efficient quantum simulators. The Gottesman-Knill theorem, a cornerstone in quantum computing, serves as the basis for optimizing and analyzing quantum circuits through character function decomposition. This method is currently being implemented in Quantum Forge, a compiler under development. The process involves representing quantum circuits as elements of a finite group under matrix multiplication, identifying the irreducible representations and character functions of this group, decomposing the quantum circuit into a sum of character functions using the decomposition theorem, analyzing the resulting decomposition to identify optimization opportunities and potential for efficient classical simulation, and applying optimizations based on the character function decomposition. Quantum Forge utilizes the MLIR compiler framework, enabling modular and extensible optimization passes. The theoretical foundations of this approach are rooted in several fundamental theorems, including the character function decomposition theorem. This theorem states that for any element U in a finite group G, it can be decomposed into a sum of character functions as follows. U equals sigma, I equals 1 to k, chi I, U, d, sigma, G in G, chi I, G caret 1, rho I, G, where k is the number of irreducible representations of G, chi I is the character of the ith irreducible representation rho I, and d is the dimension of rho I. The proof of this theorem involves defining the character function chi I as the trace of the irreducible representation rho I and demonstrating that the given decomposition holds for any U in G. In the context of group representation theory, quantum operations can be decomposed into fundamental building blocks, their irreducible representations. This decomposition reveals inherent symmetries and structure within the quantum operation, which can be exploited for optimization and efficient simulation. The process begins by defining an arbitrary vector V in the representation space and applying both sides to it, using the orthogonality relations for irreducible characters to simplify the expression. This leads to the equation, 5, which is then further simplified using another orthogonality relation, 7, to obtain the final decomposition formula, 8. The decomposition formula allows any quantum operation, represented as a group element, to be expressed in terms of the fundamental building blocks of the group structure, its irreducible representations. The character functions chi I act as coefficients in this decomposition, weighting the contribution of each irreducible representation. By analyzing these coefficients, researchers can identify which components of the group structure are most significant in a given quantum operation, leading to simplified representations or efficient approximations. This page provides a crucial step in understanding how to apply group representation theory to quantum computing, providing a foundation for further exploration and development in this field. Decomposition of a quantum circuit into a sum of character functions is facilitated by Theorem 2, which presents the necessary and sufficient conditions for this process. A crucial requirement is that the quantum circuit must be a group element of a finite group under matrix multiplication, possessing a complete set of irreducible representations over C that satisfy the orthogonality relation for irreducible representations. Furthermore, the quantum circuit must be expressible as a linear combination of these irreducible representations, with coefficients given by the character functions. The necessity of each condition is demonstrated by highlighting their importance in the decomposition theorem. The first condition is necessary due to the theorem's application to group elements and reliance on finite group properties. The second condition is necessary as it enables the decomposition theorem to express the quantum circuit in terms of irreducible representations, leveraging their orthogonality to ensure uniqueness and validity. The third condition is necessary as it explicitly expresses the quantum circuit in the required form, with character functions providing the necessary coefficients for the linear combination. The sufficiency proof constructs the decomposition by representing the quantum circuit as a group element U of the finite group G, computing coefficients C for each irreducible representation ρI of G, and constructing the sum U as a linear combination of the irreducible representations with coefficients C. By applying U to any vector V in the representation space and leveraging the orthogonality relations, the expression for U is simplified, ultimately showing that U equals UV and thus U equals U. Decomposition of unitary operators into character functions, chi, is achieved using the inverse orthogonality relation, satisfying the conditions of Theorem 1. This decomposition enables a generalized notion of quantum circuit equivalence based on character decomposition. Theorem 3 states that two quantum circuits, A and B, represented by completely positive trace-preserving maps phi A and phi B, are equivalent if and only if three conditions are met. Firstly, isometries V1 and V2 exist such that phi A, ρ, equals V2 phi B, V1 ρ V1, V2 for all density operators ρ, as shown in equation 9, ensuring the circuits can be related through isometric transformations. Secondly, the probability distributions of measurement outcomes for any positive operator-valued measure are identical for both circuits, as expressed in equation 10, guaranteeing identical observable results for any input state in measurement. Thirdly, the expectation values of any observable O are the same for both circuits when applied to any input state ρ, as shown in equation 11, ensuring identical expectation values for any observable. The proof of Theorem 3 involves demonstrating the necessity and sufficiency of these conditions. The necessity is straightforward, as equivalent circuits must produce identical observable results. The sufficiency is proven by contradiction, assuming two circuits satisfy conditions 2 and 3 but not condition 1, and showing that this leads to a contradiction. The Hahn-Banach theorem is used to establish the existence of a bounded linear functional f such that f, phi A, ρ, does not equal f, V2 phi B, V1 ρ V1, V2, as shown in equation 13. This result is crucial in demonstrating the equivalence of quantum circuits based on character decomposition, providing a novel framework for comparing and optimizing quantum circuits. The Riesz representation theorem is employed in the trace glass operator space to establish the existence of an operator O satisfying equation 14, which leads to a contradiction with condition 3 of the definition, thereby proving the sufficiency of the conditions. The character function decomposition approach can be viewed as a generalization of the stabilizer formalism in quantum computation. In the stabilizer formalism, the Pauli group Pn on n qubits, consisting of 4 n elements, is used, and stabilizer states are eigenstates of a subgroup of Pn. In contrast, the character function decomposition approach is applicable to any finite group G, decomposing its elements into sums of irreducible representations. Specifically, for Pn, these irreducible representations correspond to stabilizer states. The decomposition theorem generalizes this to any finite group, potentially leading to efficient simulation methods in quantum computation. The potential for efficient classical simulation of quantum circuits beyond the Pauli group is explored in this research. Stabilizer circuits, which are known to be classically simulable due to their structure, serve as a foundation for this approach. This suggests that similar efficiencies might exist for other groups with suitable representation theoretic properties. The Clifford group is an example of such a group, with its well-understood representation theory and the possibility of efficient simulation methods. The generalized Gottesman-Knill theorem provides conditions for efficiently simulating quantum circuits composed of gates from a finite group. This theorem includes requirements for efficiently computing irreducible representations and character values. The proof of the theorem involves decomposing the quantum circuit using character functions, showing that if these conditions are met, classical simulation is possible. This research opens up new avenues for understanding the capabilities and limitations of classical simulation in quantum computing, particularly in the context of stabilizer circuits and the Clifford group. It also highlights the importance of representation theory in determining the simulability of quantum circuits. The authors outlined 3 key steps for efficient classical simulation of a quantum circuit. Firstly, they demonstrate how to efficiently compute chi u for any irreducible representation I, leveraging the properties of characters and the assumption that each chi gauge can be computed efficiently. Specifically, chi u is expressed as a product of m terms, where m is polynomial in n, enabling efficient computation. Secondly, the authors show how to efficiently evaluate the sum pg element of g chi g-1 rho I g without explicit computation. By exploiting Schur's lemma and the orthogonality relations of characters, they establish that this sum is a scalar multiple of the identity matrix in the ith irreducible representation, denoted as C. This expression can be computed efficiently since D, the dimension of the ith irreducible representation, is bounded by p, g, for all I. Thirdly, the authors describe how to efficiently compute the expectation value of an observable O for any input state, psi. By decomposing U and utilizing the previous results, they derive an expression for psi, uou, psi in terms of chi, u, d, and g. Notably, this expression can be computed efficiently due to the efficient computability of chi, u, the polynomial bound on k, and the efficient computability of psi, o, psi, for typical observables and input states. Consequently, the authors demonstrate efficient classical simulation of the quantum circuit, enabling the computation of expectation values for any observable O and input state, psi. The generalized theorem presented in this research paper provides a framework for identifying new classes of efficiently simulable quantum circuits based on their group-theoretic properties. Building upon the generalized Gottesman-Knill theorem, the runtime complexity of the classical simulation can be further characterized based on the structure of the group and its representation theory. Theorem 5, the revised runtime complexity of classical simulation, states that for a quantum circuit composed of m gates from a group G, acting on n qubits, the runtime complexity of the classical simulation using the character function decomposition method depends on the group structure. Specifically, if G is abelian, the runtime complexity is O, k, m plus, g, 1 plus k squared plus k cubed, plus kd squared, where k is the number of irreducible representations of G, d is the maximum dimension of the irreducible representations, and G is the order of the group. If G is the symmetric group S_n, the runtime complexity is O, k, m n squared plus, g, n squared plus k squared n squared plus k cubed, plus kd squared. For general non-abelian groups, the runtime complexity is O, k, mg, g, plus, g, 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 plus k squared g, g, plus k cubed, plus kd squared, where g represents the complexity of computing character values. The proof of Theorem 5 involves defining the complexity of computing character values f, g, as a piecewise function, depending on whether G is abelian, the symmetric group S_n, or a general non-abelian group. The runtime complexity is then derived for each case, using the character function decomposition method and the piecewise defined function f, g. The runtime complexity analysis for Quantum Forge, a novel algorithm for quantum simulation, is presented. The complexity depends on the type of group G used in the simulation, with 3 cases considered. G is an abelian group, G is a finite group, and G is a general non-abelian group. For G being an abelian, the complexity is O, k, m n squared plus, g, n squared plus k squared n squared plus k cubed, plus kd squared, arising from quantum Fourier transform and group operations. In the case of a finite group, G, it is O, k, mg, g, plus, g, 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 plus k squared g, g, plus k cubed, plus kd squared, with g representing the complexity of computing the quantum Fourier transform over the group G for a general non-abelian group, G, The complexity is also O, K, mg, g, plus g, 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 plus k squared g, g, plus k cubed, plus kd squared. The inclusion of kd-2 in all cases provides an upper bound, linking the number of irreducible representations and their maximum size to the group order, capturing the worst-case scenario. Theoretical analysis and preliminary implementation of Quantum Forge yield insights into performance based on the group type and the relationship between irreducible representations and the group order. The authors present 3 theorems that form the foundation of their approach to quantum circuit analysis and optimization. The first theorem, known as character function decomposition, asserts that any quantum circuit representable as a group element can be decomposed into a sum of character functions. This theorem provides a mathematical framework for circuit decomposition. The second theorem establishes the necessary and sufficient conditions under which a quantum circuit can be decomposed using this method. This theorem serves as a guiding principle for determining the applicability of the character decomposition approach to various quantum circuits. The third theorem, circuit equivalence, proves the equivalence between the original quantum circuit and its character function decomposition. This theorem ensures that the optimized circuit preserves the functionality of the original circuit. Preliminary benchmarks are also presented, demonstrating the potential of the character decomposition method in classical simulation. Initial tests using Quantum Forge show significant speedups for certain classes of quantum circuits compared to state-of-the-art simulators. Furthermore, benchmarking on Qiskit reveals the efficacy of the character decomposition algorithm. Figure 1 illustrates the application of the character decomposition method to the Bernstein-Vazirani circuit, resulting in a significant reduction in gate count and circuit depth. The original circuit, consisting of Hadamard gates, controlled NOT gates, and measurement operations, is compared to the optimized circuit, which preserves the functionality of the original while offering potential speedups in both quantum and classical simulations. The runtime analysis in Figure 2a demonstrates the significant speedups achieved by the character decomposition method as the number of qubits increases. These results provide a rigorous mathematical foundation for the approach and promising early indications of its practical effectiveness in quantum circuit analysis and optimization. Performance analysis of character decomposition on Bernstein-Vazirani circuits. The character decomposition method is applied to Bernstein-Vazirani circuits, yielding a significant runtime improvement compared to the original circuits. A direct comparison of the runtime performance between the original and optimized circuits reveals the efficiency of the character decomposition approach. To further validate the method, measurement histograms for 4-qubit circuits are analyzed, demonstrating a striking similarity in distributions between the original and optimized versions. This similarity confirms the correctness and performance improvement achieved through character decomposition. Notably, the optimized circuits exhibit a marked reduction in runtime, making them more efficient for quantum computing applications. The character decomposition method's ability to preserve the original circuit's functionality while improving performance underscores its potential for widespread adoption. However, the current implementation is not without limitations. Future work should focus on applying the character decomposition method to a broader range of quantum circuits, as well as comparing its performance against multiple simulators to ensure a comprehensive evaluation. Addressing these limitations will be crucial in fully realizing the benefits of character decomposition in quantum computing. In quantum computing, the quantum Fourier transform, QFT, is a crucial algorithm that transforms quantum states into their Fourier transformed counterparts. To enhance the simulation efficiency of the QFT circuit, we present an optimization technique called character decomposition. This method is demonstrated in Figure 3, which illustrates the original QFT circuit for 3 qubits and its optimized version after applying character decomposition. The original circuit consists of Hadamard gates, H, and controlled rotation gates, R. Whereas the optimized circuit exhibits a reduced circuit depth and modified gate structure, maintaining the original QFT's functionality while potentially offering improved simulation efficiency. The character decomposition method has been successfully implemented in Quantum Forge, a quantum circuit simulation tool. This implementation paves the way for future research, including conducting rigorous comparisons to quantify the optimization's benefits and identifying the classes of quantum circuits that benefit most from character decomposition. By exploring these avenues, researchers can further optimize the QFT circuit and unlock its full potential in quantum computing applications. Quantum Forge, a cutting-edge quantum circuit simulator, has been successfully developed and open-sourced after rigorous testing and validation. This research focuses on the performance analysis of character decomposition on quantum Fourier transform (QFT) circuits using Quantum Forge. The results presented in Figure 4 demonstrate the effectiveness of this method for optimizing QFT circuits. In Part A, the runtime scaling comparison between the original and optimized QFT circuits shows that the optimized circuit exhibits improved scaling as the number of qubits increases. This indicates that our optimization technique significantly enhances the performance of the QFT algorithm, a fundamental quantum algorithm used in various quantum computing applications. Part B of Figure 4 illustrates the measurement outcome histograms for 3-qubit QFT circuits, comparing the original and optimized versions. The consistency in distributions validates that the optimization maintains the QFT's functionality while enhancing its performance. This is crucial for ensuring that the optimized circuits behave similarly to their original counterparts in terms of quantum state generation and measurement outcomes. Future directions for Quantum Forge include comprehensive benchmarking against other quantum circuit simulators across a wide range of circuit types and sizes. Additionally, extending Quantum Forge to handle a broader class of quantum operations, such as non-unitary operations and measurements, is planned. Furthermore, exploring applications in quantum error correction and fault-tolerant quantum computing is also a key area of interest. The optimized Grover's algorithm demonstrates a significant improvement in runtime and scaling compared to its original counterpart. This is evident from the measurement histograms, which show peak locations similar to those of the original 4-qubit Grover's circuits, confirming the preservation of the algorithm's ability to amplify the target state. The implications of this approach are profound, opening up opportunities for investigating new quantum algorithms or enhancing existing ones. Furthermore, it suggests potential avenues for theoretical work on the interplay between group theory and quantum circuit simulation, possibly leading to the discovery of new complexity classes or simulation algorithms. This could significantly advance our understanding of quantum computing and its capabilities. Figure 6 presents a runtime comparison of original and optimized variational quantum eigensolver (VQE) circuits, showcasing the performance enhancement achieved by the character decomposition method. As the number of qubits increases, optimized circuits demonstrate significantly better scaling, underscoring the potential of this approach for enhancing the efficiency of quantum classical hybrid algorithms like VQE. This is crucial for near-term quantum applications in chemistry and materials science. By expressing quantum circuits in terms of irreducible representations and character functions, the character function decomposition method identifies symmetries and redundancies, leading to more efficient circuit designs and implementations. This can potentially reduce gate count and circuit depth, highlighting the method's potential for optimizing quantum circuits. The current work lays the groundwork for significant practical advancements in quantum circuit simulation and analysis. The next crucial steps involve completing the implementation of Quantum Forge, conducting comprehensive empirical evaluations, and making the tool available to the wider quantum computing community. This will enable the development of more efficient quantum algorithms and ultimately accelerate the adoption of quantum computing in various fields. The decomposition of quantum circuits into character functions has significant implications for quantum error correction and the development of new quantum algorithms. By expressing quantum operations in terms of character functions, it's possible to design new error-correcting codes or improve existing ones. For instance, encoding logical qubits in irreducible representations of a finite group, such as the quaternion group Q8, can protect against specific types of errors. This approach also offers a new perspective on optimizing existing quantum error-correcting codes and quantum algorithms, like quantum phase estimation. The connection between group theory and quantum error correction is a promising area for future research, and the tools developed in this paper provide a foundation for exploring these ideas further. The research methodology employed in this study focuses on character function decomposition, quantum forge implementation, benchmarking methodology, and theoretical complexity analysis. Character function decomposition is rooted in the representation theory of finite groups, where a given quantum circuit represented as a unitary matrix U belongs to a finite group G. This process involves identifying G, computing its irreducible representations and character functions, and expressing U as a sum of character functions using the formula provided in Theorem 1. Quantum Forge, an MLIRBASE decompiler framework, was implemented to perform this decomposition. The compiler pipeline consists of 5 main passes: circuit-to-group element translation, irreducible representation identification, character function computation, decomposition application, and optimization based on decomposition. Each pass is implemented as a separate MLIR dialect, allowing for a modular design and easy extension of the framework. Benchmarks were conducted using the Qiskit framework on a system with Intel Core i7-12700, 32 GB RAM, and NVIDIA GeForce RTX 3050. Each algorithm, Bernstein-Vazirani, Grover's search, QFT, and VQE, was implemented both in its original form and using the character decomposition method. Runtimes were measured using Python's time module, with each experiment repeated 100 times to ensure statistical significance. The reported speedups are the average over these runs. Theoretical complexity analysis, presented in Theorem 5, was derived by considering the computational cost of each step in the character decomposition process. For abelian groups, the fact that all irreducible representations are unidimensional significantly simplifies the computation. For the symmetric group, known results were used to obtain the complexity analysis. The paper delves into the representation theory of general non-abelian groups, introducing a novel function G that encapsulates the complexity of character computation. This approach bridges group theory and quantum computing, showcasing potential for enhancing quantum computation. Data and benchmarking data will be made available upon publication, with the Quantum Forge compiler set to be open-sourced. This includes core algorithms implementing the character decomposition method, which could theoretically turn insights into practical tools for quantum circuit simulation and optimization. The authors present a comprehensive taxonomy of 17 distinct cyber-physical attack vectors on industrial control systems, categorizing them into 4 primary classes: physical attacks, network-based attacks, software-based attacks, and social engineering attacks. This categorization enables a nuanced understanding of the multifaceted nature of cyber threats and their intersections with physical systems. The physical attacks category encompasses 7 subvectors, including direct access attacks, eavesdropping, and tampering with sensors and actuators. Network-based attacks comprise 5 subvectors, such as unauthorized access, man-in-the-middle attacks, and denial of service (DOS) attacks. Software-based attacks involve vulnerabilities in control system software, including buffer overflows, SQL injection, and cross-site scripting. Social engineering attacks, comprising 4 subvectors, exploit human psychology to gain unauthorized access or manipulate system operators. This taxonomy provides a systematic framework for understanding and mitigating cyber-physical attacks on industrial control systems. By recognizing the interplay between cyber and physical components, researchers and practitioners can develop more effective security strategies to protect critical infrastructure.